So we were talking last time about greenhouse gases. So this is our first stage in our sort of journey of discovery about how inadequate the layer model is to describing the real world. The real world, the layer model has this pane of glass as an atmosphere, and all of the infrared that shines up from the ground, all of it gets absorbed by the pane of glass. So as far as infrared goes, the pane of glass is kind of an IR blackbody. And that's an assumption that we're starting to pick on now as we talk about real greenhouse gases. Real greenhouse gases are not very black. Black means that they could absorb and emit all different kinds of infrared, but it turns out that greenhouse gases are very picky about what kind of infrared they absorb and emit. So to make a greenhouse gas, there are two conditions that we need to fulfill. One we talked about very early on in the class is that the frequency of the vibration has to equal the frequency of the light. And then the other condition is that the vibration produces or oscillates an electrical dipole moment. So that means sort of having a plus on one side and a minus on the other. That's what we mean by a dipole moment. So oxygen, for example, is a symmetric molecule, and there's no plus on one side and no minus on the other, and you vibrate that or rotate it or whatever you like, it's still symmetric, and so oxygen is not a greenhouse gas. Nitrogen, the same way. The two main gases in the atmosphere, not greenhouse gases. So this was discovered in the lab by a British chemist named John Tyndall, who made a career out of measuring infrared absorption and emission by gases. So people had thought about, there was a theory for how the climate of the Earth works. The layer model actually was first described by a mathematician, a French mathematician in Napoleon's army named Jean-Joseph Baptiste Fourier, or maybe it's Joseph Jean-Baptiste Fourier. He's the same Fourier as came up with the Fourier transform, which is this operation in mathematics, and that's what he's mostly known for. But he also came up with the layer model and the greenhouse effect, and so everybody thought, well, maybe this is an explanation for the ice ages of the Earth. That this is why it used to be so cold that we now find traces on the landscape in the Alps and places like that make it look like Europe used to be sort of more like Greenland, which must have been sort of a frightening thing to discover, when they were just walking in the mountains in Europe. And so they were looking for an explanation for that, and this greenhouse effect seemed like it might be part of what was going on that made it so cold during the Ice Age. But it wasn't clear how, what part of the atmosphere it was that really mattered. And Tyndall figured out that 99.9% of the gases in the atmosphere don't do this trick. And it's just the trace gases in the atmosphere that are responsible for the greenhouse effect. So he discovered that you don't have to change the total mass of the atmosphere in order to change the climate. You just have to change these trace constituents like carbon dioxide. So we learned last time about, even though CO2 at rest is symmetric, this linear molecule, there are ways of vibrating that, vibrational modes, sort of self-sustaining, oscillations ringing like a bell that do create an asymmetry and create an electrical dipole. And the one that's most important is the bend. So both oxygens go up and the carbon is down, and then it goes back the other way and sort of boing, 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 boing like that. That mode of vibration of the CO2 creates an electrical dipole, sort of minus on one side because there's more oxygen on one side and plus on the other side. And as a result, that mode of vibration is what we call infrared active, and so that does Fourier's trick of warming the climate. But now, how exactly do we take these choosy gas molecules and kind of plug them in to this oversimplified model? That's where we're going today. So, the first thing I need to show you is kind of like a housekeeping thing almost. We talked about different units of light. So there's frequency, and there's wavelength, and they're both, those are both interconvertible. So if you know the frequency, you can calculate the wavelength. You did that in lab the first week. It turns out that in science, people specialize, and so they focus on particular parts of reality. In this case, the different kinds of light, and try to sort of set things up that are convenient for themselves. And it turns out that people who study infrared light, even though it's the same kind of phenomenon as all the other different kinds of light, they have come up with kind of their own a different way of describing light, and it's something called the wave number. Which is defined as the number of cycles per centimeter. And so if you knew the frequency or the wavelength, you could calculate the wave number. It's just another way of measuring the same thing. But it turns out that for infrared light, this gives nice numbers that you can hold in your head without too much pain. So the CO2 bend, for example, takes place at a wave number of about 700 cycles per centimeter, or I've done the sort of abbreviated thing of leaving out the cycles and just writing centimeters to the -1, which just means 1 over centimeters. So this is equal to cycles per centimeter. So we're going to be looking today at output from a computer model that you run from the web that you will actually be using in lab next week. And the units of light on that model, it turned out to be convenient to use wave numbers, even though it's confusing because it's yet another metric. But it made the plots sort of a nice shape that you can look at. So just so you know what those units are. A high wave number, this has a symbol N. A high wave number means lots of waves in a centimeter, and so that's equivalent to a high frequency, because if you have lots of waves and they're traveling at some speed, then that's lots of waves per second. And it's also a sort of short wavelength. So let's do something like a layer model, but instead of a pane of glass there for an atmosphere, we're just going to have a little cloud of CO2. And then there will be light coming up from the ground. But we can't think of it all as the same stuff anymore because the CO2 is going to be selective about what it does to this light. So I'm going to draw let's start without CO2 first. Two different arrows coming up, and one of them is going to be at 700 cycles per centimeter. So that's an absorption band that's a kind of light that CO2 can absorb and emit. So it acts like the pane of glass. And then I'm going to draw another one, which is going to be at a different frequency, 900 wave numbers, 900 cycles per centimeter. And this 900, it turns out, is going to be a part of the infrared spectrum that the gases, there just don't happen to be any gases at all that absorb that. So this is a color of infrared light, if you let me call it that, called the atmospheric window. The atmospheric window is at 900 centimeters, inverse centimeters, 900 cycles per centimeter, and the CO2 bend is at 700. So if we were to now add the CO2 cloud, the CO2 will absorb in the bending frequency, and then it will re-emit in that frequency. Whereas the 900 centimeters, the CO2 doesn't touch it, and it just goes right from the ground. So it's like we have a pane of glass, but it's just selective now about the light. So if we draw a Blackbody spectrum, we have intensity, the brightness on this axis, and then this will have as the wave number, so high wave number out here, this is also high frequency. And a Blackbody spectrum kind of looks like that, right? It's just a hump. You know, we've changed the shape of the hump maybe by using different scale here, but you know, it's still sort of a hump. There's a maximum intensity, and the area under this curve is equal to the total energy, and if we were to heat it up, the area would expand according to sigma t to the fourth, and then the peak intensity would shift toward the shorter light wavelength light. You know, so if we heated it up high enough, it would start to get into the visible light, and we would be glowing like the sun. So this is all stuff you've seen before. So let's say that this black body is what you get at the temperature of the ground. And we're going to put on this black body labels for our two different kinds of light, so we can keep track of what's going where. And so 700 is about here, kind of at the peak, and then 900 is a little bit off the peak, like that. So now I'm going to draw another black body curve on this same diagram that will be the black body curve for the temperature of the atmosphere, which we're going to assume is colder than the temperature of the ground. So the pane of glass was colder than the ground in the layer model, and it turns out in the real world it's colder up high in the atmosphere than it is at the ground too, but there's some interesting stuff going on that we'll talk about that in a couple more lectures about why it gets colder with altitude in the real world, because you haven't heard the whole story on that yet either. But for now, we're just going to say this is cooler than the temperature of the ground. And so that means that a blackbody curve for the temperature of the atmosphere will be smaller than the blackbody curve for the temperature of the ground. And so epsilon sigma t to the fourth, is smaller because the temperature is lower and all that. It's a blackbody curve like you've seen before. Okay, now standing up in space, or flying or whatever, orbiting, looking down at the Earth, so there's our eyeball, which is our generic, sensor. If we look down at the light that's coming up from the ground, in the 900 wave number part, we just see the ground because the air is transparent in the atmospheric window frequency. So it's like you're standing on a boat and looking down through the water, and the water is totally clear. What you see is the bottom, the mud at the bottom. So what that looks like under 900 centimeters, the intensity that we'll see is the intensity from the blackbody curve from the ground. So it's going to be kind of right there. Once in a great while, it's worth colored chalk. There. Now, if we continue looking down at the Earth from space, from our eyeball, and we look in the color of infrared light of 700 wave numbers, that's a wavelength that the CO2 absorbs and emits. So that's as if we're looking down and seeing the pane of glass. So looking down at 700 wave numbers, we get an intensity that sort of follows the black body for the atmosphere, which is colder. So it's looking kind of like that. Now, the other frequencies, there are other gases that absorb, but this is kind of the main story. The real infrared light that you see coming out of the Earth, if you look down from space, is going to kind of be between the warm black body and the cold black body. And whether you see the warm black body or the cold black body depends on what gases there are in the air that absorb and emit infrared. So in the atmospheric window, you see the ground. In the CO2 bending vibration frequency, you see the CO2, which is colder, and so it's following this colder blackbody curve. I'm going to leave you to think about whether this makes sense for just a half second while I lower the screen. So here is the model that you'll be playing with in lab next week. It has sort of inputs on the left side there, including a CO2 concentration, which is set at 375. And I ran the model, and this is what we get for the output. There are 5 different blackbody curves on the screen there for different temperatures. So 300 Kelvin is the green one, it's the warmest, and then 220 Kelvin is the yellow one, it's the coldest. And as you ramp up the temperature, you see that blackbody curve kind of bulking out, right? Because sigma t to the fourth goes up as t goes up, and so the area under that curve has to get bigger. And there you go. The atmospheric window is right about 900 wave numbers, and it's sort of right through here. And what you see there is the warm ground. The ground here, the ground temperature, it says, is 299 Kelvin. And so the intensity of the infrared that we're seeing in that frequency range is very close to this green blackbody curve for 300 Kelvin. So we look down and we see the ground. It's like standing on the dock looking through the lake and seeing the mud at the bottom because the water in that frequency is clear. This is the CO2 bend right here, that big sort of bite that's taken out of the spectrum. And in the center of that CO2 bend, what you see is 220 Kelvin, which is the yellow curve, which is the temperature up in the upper atmosphere. So let's try getting rid of CO2 here. Set it to 0 and rerun the calculation. Now, the atmospheric window sort of continues on through there. There's no more CO2 in the air, so the CO2, it's like we kill this, we get rid of that, and then the arrow comes all the way up from the ground now, and the ground is warm. So what we see at 700 wave numbers on this scale here is something that looks a lot more like the green black body from the ground than like the yellow black body for the cold upper part of the atmosphere. Anybody? You guys are easy today. Oh, yes, there's a question.
Does it mean that something, if it is an atmospheric window, what is that you can see through it? Or
So the question is, yeah, what does it mean, atmospheric window? It means that there are no gas molecules in the atmosphere that can absorb or emit light in that frequency range. So it just happens to be, the atmosphere happens to be transparent. I mean, it's kind of funny to think about a window as infrared because we don't see an infrared, but if it was invisible, it's as if just the green light would get through or something like that. So if you go swimming deep down, and especially if you take pictures, what you find is that everything just looks very blue because the red light gets absorbed by the water, and so you have to color correct your photographs to make them pretty, or not go too deep where there's still some red light. So you could sort of call blue the water, the window in the water. That's the light that can get through the water. So that's what we mean. Okay. So there's two different points that I want to make. Two things I would like you to understand about how this works in the rest of today. One is that adding CO2 decreases the infrared energy output. So we'll put the CO2 back in, and you'll see it take that bite out of the spectrum, and the total energy output is given by the area under the red curve there, which is kind of a more complicated thing to measure now because it's all spiky because there's other gases in the air. But so no CO2, the area under the red curve is larger, and the total energy out is given up at the top there. The intensity of the light is 318.39. 318.39 watts per square meter. So now we're going to put CO2 back in there, 375. Actually, the real CO2 in the atmosphere is more like 385 now. It's going up at about 2 ppm every year, so this model is just a little bit out of date, you can tell. So I put the CO2 back in there, and it's now driven this red line way down, there, and so the total area under the red curve is less than it was. And the intensity, it says up at the top, is now 287 point something, 0.84 watts per meter squared. So the CO2 is preventing light from escaping. It's slowing down the rate at which energy leaves the planet. But now, from the layer model, you know that ultimately the planet has to balance its energy. What comes in has to go out. So if we draw another one of these plots in a sort of a schematic way and imagine doing things kind of one step at a time, we'll start out with no CO2, and the energy just leaves from the ground and goes to space, and it's 318 watts per square meter, and it looks something like that. Now we add CO2. So we have to think about the two different kinds of light now, 700 and 900 wave numbers, and the CO2 absorbs, and it takes that bite out, and so now here's the bite. So here's sort of scenario 1, scenario 2 is there, 1, 2. And so there's less energy leaving the Earth than there was before. And what happens then is that the Earth has to warm up in order to balance the energy books. It's like the sink. It's like putting the obstruction in the drain of the sink. You put a piece of cucumber on the drain, and suddenly water is draining out more slowly, and you've got water flowing through all the time, but it's got to ultimately balance the flows, and so the water level in the sink gets higher. How that looks here, I didn't leave myself quite enough room on the board to draw this nicely. How stupid of me. Let me do this. So there's 1, 2, and now we have to warm up the ground in order to balance the energy again. So we warm things up, and so the Blackbody curve for the ground gets a little bit higher because the ground is now warmer, and there's still this bite. But the total area under the curve can expand kind of here by warming up the ground to compensate for the area that it lost because the CO2 took a bite out of it. So it's like the layer model. If you started out and everything was in balance, and you suddenly put a pane of glass there that was colder, the energy flux would be out of balance. The Earth would warm up until it could balance again. Here it's doing the same thing. So let's see. There's a temperature offset on this model. So if we wanted to make this look so that it had 318 watts per square meter again, we can probably do that by warming it up. So I'm going to try. I'm going to try 2 degrees centigrade. So that gets us up to 295 degrees, or 295 watts per meter squared. It's not quite enough to 298. Okay, so there we've got to 317 degrees and 317 watts per square meter. So the red curve here has kind of inflated. Can you see that? So if we go back to not changing the temperature, watch the red curve. It'll get smaller. And then I'll take the CO2 out. We'll lose the bite. And the total energy out is the same. So adding the CO2, even though it's selective about the light, it acts just like that pane of glass in the greenhouse, and it makes the Earth warm up in order to balance the energy. So that's one of the 2 points that I wanted to make today. And everybody seems to be content with that. That's good. Yes?
What's the area under the curve again?
The area under the curve is, what did I do with my? The area under the curve is, by the way the graph is constructed, the area under the curve is the total energy. In watts per square meter. So if we were to do the area under the curve, one of these smooth curves here, a Blackbody curve, the area under that would be sigma t to the fourth. So it's a way of eyeballing, the energy by looking at the plot. It's constructed in that way to kind of make it convenient so that you can kind of, connect. Look, that took a big bite out with watts per square meter, because the total watts per square meter, 318 here, is that whole blob. Okay, the next interesting thing that arises because of this is a phenomenon known as the band saturation effect. And the band saturation effect, the bottom line is that it makes trace gases like methane, or in even more extreme case, freon or sulfur hexafluoride, or these various other industrial chemicals. It makes chemicals that are in very, very small concentrations much more important than you would think they would be, just given the number of molecules. So I want to show you what this means by doing a series of experiments here with this model. So we're going to change the CO2 concentration sort of one step at a time and measure, or let the model tell us the intensity of the light leaving to space in watts per square meter. So 0 ppm, we already had up there. The intensity is 318 point something, 0.4. So I'm going to do a series of these things, and we're going to write down the numbers, and I'll make a plot. So adding 1 ppm now of CO2, and you start to get just a little bite out of it. The CO2, there's only 1 parts per million CO2. This is about how much methane there is in the atmosphere. So it's sort of a trace concentration. And the bite that you see is in the same place, but it's a little smaller, because some of the light that's coming up from the ground can escape through this CO2. There's not enough to really absorb all of it. You can get some of it. So you see a little bite there. And the intensity of light has dropped to 313.8. Go to 10 ppm and run it. And now the bite in the spectrum has gotten bigger. CO2 is getting a little greedier. It's almost starting to reach that yellow line down at which is sort of the intensity that would be coming from the upper atmosphere, but not quite. So right in the center of the absorption band, right in the center of the frequency that CO2 can absorb, what you see is sort of the top of the atmosphere right there. But it's not really, it's just a little spike that sort of gets close to that, and the peak is still sort of narrow. And let's see, the energy intensity going out, the total flux is 305.5 watts per meter squared. 305.5. Go up to 100 parts per million, and so now the bite has sort of gotten a little bit wider, and it kind of more decisively hits that yellow line there. So a bigger part of the spectrum is sort of completely absorbed, and all you see is the upper atmosphere, and then the fringes, the edges of the peak have gotten wider. So if we just go back to 10 from 100 here, watch the thickness of this peak here as we back down to 10 parts per million. See, it's gotten skinnier. Now we go up to 100, it's gotten fatter. And we recorded, I think, no we didn't, but at 100 parts per million, the intensity is 294.1 watts per square meter. And then one more, 1,000 parts per million. Run it, and it's not really getting any deeper. In the center of that band where the CO2 absorbs, basically what you're seeing is the top of the atmosphere. So the intensity, the bite that the CO2 takes can't get any deeper than that, but it is getting wider. So 1,000 takes us to 283.3. 283.3. Okay, so let's plot the intensity as a function of the CO2 concentration. So there's going to be 1,000 parts per million, and here's 0. So 500, 100, 10, da-da-da-da-da. And with the vertical range, we got to go from 280 to a little less than 320 watts per square meter. So we'll just make a plot here. So at 0 parts per million, the energy going out was 318, sort of right there. 1 part per million, which is like not even that much different from 0 on this plot. Let's see, so 280, 290, that's 290, 300, 310, 320. So at 1 part per million, we've dropped all the way down to 313. So it's kind of right there. 10, we've dropped to 305, and 10 would be still very close to this still close to 0. 100, 294. So 100 is sort of here. 294 is about there. And 1,000 has dropped to 283, so it's like that. So we'll connect the dots and see that it's not a straight line at all, is it? It's a curve. So what's happening is that when the concentration is low, the light that the gas takes out of the spectrum gets deeper and wider when you add more. Whereas if the concentration is high, the bite only gets wider. Okay, so the first question is sort of a deep review. We're going back to the sink analogy. So the water level in the sink, what does it stand for in the kind of analogy world? Is it sunlight, heat energy, infrared light, or Earth's temperature? What do we think? Let's look and see what we think. Well, still some more votes coming in. That's good, because heat energy and Earth's temperature are basically the same thing. Earth's temperature is telling us how much heat energy there is. So there's two right answers here, and now one of them is beating the other by mere sort of social peer pressure. But you know, when I first turned on the thing, they were both sort of equally represented. That means you guys are right on the ball. Okay. In the sink analogy, if we were to sort of combine the sink analogy with this plot that we've been looking at today, where on this plot are we going to find the water level in the sink? So there's A, B, C is up there, and D. The water level in the sink, remember, what is it? It's the temperature of the Earth's surface, or the heat energy, the heat content of the Earth's surface. So where do you see, if we change the temperature of the Earth's surface, where do we see that in this plot? Where, oh where? We see it there. So let's watch it in action again. So I'm going to add 10 degrees of warming to this model and look and see what happens. And there, that's the atmospheric window. So that's the place you can most directly see it. I mean, maybe you see it every place, you know. So nobody said these questions are going to be all that fair, but that's kind of what we were looking for. Okay, so CO2 in the air is akin to what part of the layer of the sink analogy? Would it be the faucet, the water level, obstruction in the drain, or the drain itself? And it is, in fact, an obstruction in the drain. You are absolutely right. So, the next obvious question is, where do we see the grape in the drain? Sorry, I've been doing cucumbers with you, and I did grapes last year, so, we just have to deal with that cognitive dissonance. Where do we see it? Yes, of course, this is the CO2 absorption band. That's how the grape or the piece of cucumber is, that's how much energy, water is not flowing through the drain, is given by the area of that peak right there. So, very good.